Hey guys, this is my second video of examples for finding increasing and decreasing functions and using the first derivative test. So in this video we're going to start with f of x. So as a reminder, you want to pause and try the examples when you are prompted so that you can stay really engaged with this video, and there are free guided notes available at divideandconquermath.com. Alright, so in the examples we're going to talk about, we want to identify the critical points, identify the intervals of increasing, decreasing, and then identify any local or global max or min values if possible. Okay, so with these examples, I'm going to give you the function and then you've got to figure everything else out. So this is calculus. We're probably going to have to take a derivative, right? So let's start by taking a derivative. So this one is a nice and straightforward derivative, and so now I've got to find my critical points. Now, it's here that it's a good time before you start getting too far into this that you just consider what is the domain of your function. So just in looking at this, my domain is all real numbers. So I actually want to just note that so that there is no restriction. I can really kind of do whatever I want with this. So this is kind of one of the nicer problems when you don't have domain issues to worry about. So because of that, the domain is all real numbers. That means there's no place where, and this is a polynomial, there's no place where this is undefined, so we just have to worry about finding the critical point. So that's step one here. So we find the critical point by either finding where the derivative is undefined or where it equals 0. So in this case, I'll just set my derivative equal to 0. And I would get in this case that this will equal 0 when x is -1. Okay, so this is pretty nice and straightforward then. So what I need to do now is I basically need to chop up my domain around my critical point and create a table to kind of organize all my information. So I'm going to have my intervals listed out here, and then I also want to note the sign of f prime with this. And so now I'm going to draw a number line just to kind of help me with this. So my domain is all real numbers, and my only critical point is here at -1. So this is kind of how my intervals are going to be divided up. So my first interval is going to go from -infinity to -1. My next interval will continue on from -1 to +infinity. And so the idea with this is that all of the critical points kind of define where the function might have a change in behavior. So if I find one test point in here and test this out, basically any other point in this interval is going to have the same sign of the derivative. So let's say for a second that I decided to use, how about x equals -2. So what happens if I have x of -2 and I plug that into my derivative? Well, you can actually work this out, but I've talked about this in the previous video as well. The real thing you're trying to figure out here is this going to end up as something positive or negative? So this can take you a long time sometimes to compute this. The big thing is just, is this positive or negative? And we can see just by looking at this that this is going to be negative. Then on the other side, so this is for the first interval, so let's go to the next interval. So a good test point for the next interval would be 0. So let me clear some space. And now we're going to use x equals 0. And so if I just plug in 0 into this, I see that I get 8, so this is going to be something positive. Okay, so now we can discuss part 2 of this problem, identify intervals of increasing, decreasing. We have enough information to do that. So let me clear some space. So this table makes it nice and straightforward to answer that question. Basically, if the sign of f prime was negative, then that means that we have decreasing here, and if it was positive, then we have increasing. So let me just summarize that. And you do actually want to take the time to write this out in a nice clear-cut sentence so that your instructor knows exactly what this table means. It's kind of like you would never send this table of information to your boss. You would just summarize what your boss wants to know. So you want to just make sure it's very, very clear that you understand what all of this means by writing this nice complete sentence. Okay, so now we can move on to the last part of this, identifying any local or global max or min values. So let me clear some space. Alright, so this will require us to use the first derivative test, which I will remind you of. So for the first derivative test for local extrema, when you have f of x, a continuous differentiable function, and you've got all its critical points, here's what it says. If f prime changes from positive to negative at that critical point, then you have a local maximum. If it changes from negative to positive at that critical point, then you have a local minimum. So in this case, oh, and then of course there's the third one. If the signs don't change, then you don't have anything. So in this case, notice then I'm going from negative to positive. So what this means is that I have a minimum. And this is all hunky-dory in this case because our domain was all real numbers, so everything kind of works. And if you think about this for a moment, what is the graph of our original function? This is just a parabola, and it's a parabola opening upwards, so you should have a minimum. So intuitively that makes sense because we kind of know something about this graph anyways. So let's just summarize that. There is a global minimum at this point, negative 1, 9. Now, another way that I could phrase that is that the global minimum is 9. So you want to make sure that your language is nice and clear with this. This can be something that's a little tricky and it's easy to get a little sloppy with. The minimum itself is 9. It occurs at negative 1, 9, or it occurs at x equals negative 1. So just be really careful in your language. That's one thing that can be a sticking point for some people. And also we know that this is a global minimum because just think about the nature of how this graph actually works, right? This is going negative and then it's going to turn back up and be positive. That is, if I try to map out what it means to go from decreasing to increasing, it's going to look like this. This is the actual graph of my function. So whatever this point is, it must be a global minimum. So that's the kind of information you're looking for when you want to make a clarification. If you want to classify something as a global min or max, it has to be something where it's like really clear cut like this. Okay. So now let's move on to something just a little bit trickier. So in this example, maybe before we get started, let's first just note the domain here. So I have got x squared e to the negative x over 3. And the domain of this actually is going to be all real numbers. There is no value that you can put in for x that will make this thing equal 0. And you might be thinking, oh, this is actually just x squared over e to the x to the 3. But there's just nothing that you can actually put in for this that is going to make this e equal 0. So the domain in this case is just going to be all real numbers. Okay, so now let's continue on to finding the first derivative. So I'll clear this out. And why don't you pause the video here and find the first derivative and hit play when you're ready. So the first derivative, when you find it, okay, so here is kind of the general structure of it. But the thing about working with these problems is that you're a lot of times going to have to use algebra to make them nicer to look at. So remember, I have to figure out whether or not this thing has any areas where it's undefined or where it equals 0. And the reality is, in just looking at this is just not very nice to look at. So you might want to kind of mess around with this a little bit. So if you need to, pause the video and then clean this up a little, hit play when you're ready. So if I try to actually make this look nicer, so I can rewrite this without any negative exponents if I wanted to. I could also factor out the e to the x to the over 3, but I'm going to write it like this. And then from here, so it's not going to be that much work for me to get a common denominator, and it will make my life a lot easier. So I'm just going to multiply this fraction by 3 over 3. So ultimately I get 6x minus x squared over over 3 e to the x over 3. And so now this actually makes my life a lot easier. So let me just replace this as my derivative. And now let's actually go through and find some critical points, huh? So we have to figure out where is this either 0 or undefined. So figuring out where this equals 0, I just have to worry about where does the top equal 0. So if I set the top equal to 0, I can factor this. So I've got 6x minus x squared. This is going to be x times 6 minus x. So where does this equal 0? Well, I have a critical point then at x equals 0 or at x equals 6. Those would be my two critical points in this case. And I don't have to worry about this being undefined. Again, there's just no x that you can plug in that's going to make e equal 0. It's just not going to happen. So these are my two critical points. So maybe I'll just note that. CP at. Okay, So next thing, we've got to make our table. So if you kind of feel like you've got it from here, maybe pause the video and see if you can finish this. Otherwise, I'll kind of walk you through everything. So first we've got to create our table. So we know that we're going to have our interval and our sign. And so now what we've got to do is determine how to kind of slice up our interval. So this is where we remember, oh, okay, my domain is all real numbers. So if I just order a number line just to see how this will get cut up. So my first interval is going to go from -infinity to 0. My next one's going to go from 0 to 6. And then my last one's going to go from 6 to infinity. So there are my pieces. And now I can start choosing test points. So maybe you want to pause the video now and choose some test points and try to fill in the rest of the table. Hit play when you're ready. So once again, you want to try not to get too bogged down with like what the actual answer is. If I just kind of try to think about what happens at the derivative at f prime of -1, which would be this first interval here. So if I just think about kind of how the top of this factors, I'm going to use it like this. So I'm going to do -1 times 6 minus -1, all of this over 3e to the -1 over 3. Okay, so what you really care about here is just the sign of this. So this is negative, right, times something, this will end up being something positive. And then this 3e to the -1, this will also end up being positive. All this negative exponent is going to do, it's just going to bring this back up here. So ultimately, the sign of this is going to be negative. And so that's what you want to do for each interval. So if I plug in something like, say, x equals +1, so then everything's going to be positive, so this will be positive. And then if I put in something bigger than 6, so when I plug that into the top, it's going to make the whole top negative, so this will end up being the sign of the derivative will be negative again. All right. So now I'm ready to just say where my intervals of increasing and decreasing are, so let's do that. And so there you go. So that's going to answer that question. So now let's just work on the last part of this, identifying any local or global min or max values. So let me clear some space. And so using the first derivative test, so this is going from negative to positive. So here I'm going to have a minimum, and then I go from positive to negative, so then I'm going to have a maximum. All right, so now to summarize. Okay, and so I just kind of wrote this out. Maybe I wasn't as clear in the last example. So when you state that there's a local minimum, so this occurs at the point 0, 0, and the way that I find that is I plug that point back into the original function. So same thing for when I state my local maximum. So my maximum is at 6. So this occurs at f of 6. So I plug 6 into this thing here, and I got 4.82. So I have a local maximum either occurring at the point 6, 4.872, or, you know, if you want to think about it from a functional standpoint, you're plugging 6 back into the original function, not into the derivative. Because this whole thing is about categorizing behavior of the original function. So you're ultimately not trying to just put it into the derivative. That's kind of it. Okay, so if this was helpful, please consider giving my video a like or subscribing to my channel. Consider sharing my channel with your friends. That will super help me. If you have any feedback, consider leaving me a comment. And otherwise, thanks for watching. And I will see you guys in the next video. In the next video, I talk about more difficult situations with this type of problem. So I'll see you guys next time.